So everyone, we're now going to jump in and start understanding what's going on in some of the contracts. We're going to make our first contract already. So I've got some steps here. So we're going to go to EOSIO. I'm going to just start us off afresh. So first thing you want to do is log in and then create a new project. Oh, shit. I'm going to delete one of my projects. Okay, so create a new project and just call it like Hello World 11. That's fine. So this here is the header file. So this defines the contract. Here is the implementation of the contract. So now what we're going to do is we're going to compile the contract by pressing this button. So hopefully it doesn't take too long. Looking good. Yep, looks good. So now we've got the ABI and the WASM file here. You're welcome to look at. Now I need a new account to deploy this to, where that contract's going to live. So we create a new account. I click create account here. Before you do that, you need to make sure you have some keys. So go down here, this green one, and create a new key pair. Right, I don't mind showing you this because it's only on this EOSIO. So save that. I'll use this new one starting with JAN. So a new account here, and you might have to search around. Hello 2222. Okay. So you need to create a name here. It has to be less than or equal to 12 characters. You might have to figure out which ones are available. It doesn't really matter too much at this stage. So I create that account. Now if I want to look at that account, I can go to it here, and then I click on account. So I can see that account here. I can see what transactions have been made to it by refreshing this. I can look at the contract deployed at that account here by clicking on contract. You can see here that the contract has not been deployed yet. So this is all running on a single node testnet that's running here. So this is just a one node EOSIO chain run by EOSIO. It actually performs and runs almost the same as any of the decentralized networks as well. You can see here it's creating a new block every half a second. So back to our project now, we've created this account. Now I want to deploy the contract there. So I click this deploy button, and I can deploy it to my new account I just created, Hello 222. So now if I click here, that's already been deployed, and the transaction, I can see this new interface pops up, which has all of the actions defined in the function, as well as the tables defined in the contract as well. So this is the memory of the table. So I'm going to call one of the actions. So I'm going to call the hi action hello 2222 with the same account. I'm a string. I'm going to execute that by pressing play. You can't quite see it down here, but this shows the transaction ID. Yeah, there. I'm going to make this a bit bigger for you though. So if I click down on the transaction here, you can see the action called. You can see what was changed within the contract in the table. And I can, if I refresh the messages table now, see that there's a new row in the table with the message I sent. Lastly, if I go look at account now, I should be able to see, if I refresh this, yes. So here are the two actions where I deployed the new contract. Here's the transaction I just sent. I can click on this again and it shows me that same data. Right. So walking through this contract, so we saw the header file, the HPF file. So we're just going to walk through what's going on here. Essentially, this file defines the actions. So these are the externally facing functions that other contracts and other accounts in the system are able to call. And it defines the data structure that's used in the table, and this is the persistent storage available to the contract. All right, so those are the two main things. So we're going to walk through this line by line. So up here, it includes the EOSIO library, and that contains all of the classes, the types, macros, and everything else needed in C++. It's a C++ library used for EOSIO smart contract development. Everything you need to know about what's included here is in the EOSIO library API, so you can find that on developers.eos.io, which also has all of the other documentation for all of the other tools and products they've built. If you're interested, this is the actual source code for the library, so you can see exactly how this works. So the next part is it declares the use of these namespaces. So this is the standard C++ library in the EOSIO library. So that means instead of fully declaring a string as being part of the standard library, you can just write string. And equally, you can do the same thing with the EOSIO contract class. You can just write contract now. So now we declare the contract. So we use this macro here, all caps contract, so that's a macro, and that expands pre-compiling to this. So we can see now that this is a class called Hello World 1.1 that inherits from the public class contract. Now this part here, EOSIO in the double square brackets, that's a pre-compiler attribute that tells the compiler a few bits of information that helps it create the ABI and a few other things. So what happened when we compiled this? We used a special tool called the Contract Development Kit, and that compiled the C++ code, including the header file, into a WASM file and an ABI file. That's the application binary interface. And that was done by calling two transactions, setCode and setABI, on the system account. And that deployed this contract in this format to an account, the account that we just created. So that WASM file is something special. So WebAssembly is a special stack-based virtual machine. It's an execution environment, a very efficient one, designed for the web. It's actually being led by the four major browsers, Safari, Firefox, Chrome, and Internet Explorer. So these are the goals of this virtual machine execution environment. It's meant to be fast, efficient, and portable, meaning that it runs the same on all different types of clients and all different types of web browsers. And the only other execution that's available in web browsers we know is JavaScript, which is very not efficient and not very portable, as in JavaScript does not necessarily behave the same on different browsers. It's supposed to be readable and debuggable, so useful to write code in. It's supposed to be secure, so it should provide a sandboxed environment. And it should be backwards compatible. It shouldn't break the web as we know it. So WebAssembly is what the C++ programs compile down to in the end, and that is run in the WebAssembly execution engine on the nodes. Now, a big part of so WebAssembly is actually now used in a lot of different blockchains, like the Parity client and several others, because of these properties, because it's fast, it's standardized and mature, and importantly, it's portable, meaning that it runs to the same result every time. So this is the deterministic characteristics required by blockchains we're going to learn a bit more about later. The ABI file, this is a file, actually it's in a JSON format, uploaded to the blockchain, and it basically describes what's in the contract, how to call actions on it, so what arguments do actions take, and also importantly, what are the structures that the tables contain. So this allows other accounts and contracts to call the contract as well as read the contract. So that's what the ABI is for. So in the private section is where we declare the structure for the data that's going to be in the EOSIO database, and its initialization and types. So in that public section, this is what we've got. We declare two actions that can be called by other contracts and accounts. One's called hi, which is what we just executed, and it takes two arguments, a name called from and a message string, and another action. So action here in capitals here is another macro. It expands to this with another precompiler attribute that allows the compiler to generate that ABI automatically, and also void. This is the return type of the function. So this function does not return any type. It's void. So who here kind of knows about digital signatures, how they work, why we use them? Show of hands? Yeah, okay. So we're going to go through this reasonably quickly. So this is a piece of cryptography used in most blockchains for authenticating messages. So in this scenario, it uses asymmetric cryptography, which requires two different key pairs. A public key, which you can share with everyone else, and a private key, which is kept private to you only. So this is just one type of cryptography, digital signatures, and the way that it works is with my private key that nobody else has, I can sign a message, a piece of data, and then anybody with the public key who I've shared is able to verify that only the private key could have created that signature. And that allows anybody to authenticate with mathematical guarantee that only whoever controlled that private key created that digital signature. So that allows us to do authentication without actually sharing the whole password, for example. It allows me to keep part of the data to myself, the private key. That is never shared with anyone else. So what happens in our blockchain application now is we get our piece of data, and we want to call one of the actions on that smart contract. So we're going to call the hi action, and we create a piece of data with the hi and its arguments, so the from and the message. And what we do is we create a digital signature of that piece of data, and has to be signed by the private keys associated with that account, Hello World 11. Now that's sent to one of the nodes in the network. In our case with EOS Studio, they're running a one-node blockchain application. So it's very simple, but the process is the same for a decentralized network like EOS or Telos or whatever it is. So they send it to one of the nodes in the network. That node then puts it into the EOSIO protocol, and that synchronizes it across all of the nodes in the network, if that exists. It will synchronize the data, and it'll put that into a transaction ledger, the history of all the operations, and update the EOSIO database as needed.
How the blocks, what is the time to update the...
So the block time in EOSIO is 0.5 seconds, half a second.
Very fast.
So everybody adds this transaction to the ledger. They update the EOSIO database, whatever tables got changed. And then, unlike regular databases, each node is run by different entities. And each node can participate in creating the consensus across the network of synchronizing that data without having one party in full control. And because of the cryptography, because everybody can verify the signature, because everybody can verify the blocks, which we're going to get to later, this is done in a way that is extremely easily to detect if somebody's manipulating the rules, and then they stop synchronizing them. Any questions about that process? Yeah, we're going to go further into it in a bit. Yeah?
Does everyone have to have the whole blockchain on their server or their node? Like, or can you access it through an app, smartphone app or something?
Yeah, absolutely. So so the question is, does everybody need to run a node? So generally, a front-end client does not run a node. It interacts through an API exposed by a node. If they, often for startups, they'll use somebody else's node because running a node has costs associated with it. If you don't want to trust any other nodes, you run your own node, let your application connect to that, and that node you have your full guarantee that you're running the right software, and you know that that protocol is enforced by that software properly. So you know that you're synchronizing the right database.
Do you run a node?
I do not run a node. Well,
A person?
One guy from the
I know there's. Do you guys run a node? Yeah, Effect AI runs a node. Is that a full archive node?
Not a full archive node.
No.
No, I don't think many of those exist anymore because it's too heavy. If you want to keep track of the entire history of the EOSIO blockchain, it's very, very heavy application.
Yeah.
But you can just keep track of the current state, so that's sort of the lighter.
Yeah.
You still have the guarantees.
So like for Ripple, they say that they can. No one rolls the node, only Ripple. You know, like if you ask for it.
Yeah, it could be. So I mean, all of the block explorers run a full archive node. They have to have the entire transaction history, and there's at least 5 of them, and I'm sure there's more archive nodes out there. But there's lots of different EOSIO databases, so the answer depends on which blockchain you're talking about. So let's move on. So this here is the definition of the data that goes into the EOSIO database. So here we have a name, a string. So table here is another macro. It expands to this. It defines a struct. So this is a primitive in C++. And again, another precompiler attribute that helps it generate that ABI. So this is the data structure. It has 2 variables. Pretty easy to understand. This is what it stores. And it has what's called an indexing function. And this allows us to query the database efficiently. Each data structure has to have at least one indexing function, but it can have multiple.
Going very fast in some of these things.
Yep.
I can barely even read I'm trying to understand the first part, and I know there's text below, so okay, focus on the first part, okay, I'm trying to understand that.
Okay.
And then there's other stuff that you should also know.
I'm just...
Am I the only one that's having trouble keeping up? But this is, whoa, sometimes goes very fast.
I can slow down. Just let me know. I'm basically saying what's on here in a different way often.
You're trying to walk, like the way I'm looking at this, you're walking us through the concepts and then high level. Right?
Yeah.
And so like later.
Yeah, I mean, we're going to build it up all day. There's a lot of things going on here to understand. Yeah, we're going to go, I mean, I'm going through code because we're all his developers, and it's going to make sense.
If I'm the only one that's struggling to keep up, then...
So this is the structure for that EOSIO database. This stores a table in the database, and this is the structure of that table. So this defines the columns of that table, right? And this primary key, it connects to this value user here, right? So this user is a particular type name. We're going to discuss that in a second. And it defines an indexing so that you can search this table by the user. So then we can run queries in smart contracts that let us find rows in the table based on their user name, essentially. And it can do that in an efficient way. Yeah.
The definition that you are making here with the user in the text, it's for your application.
That's right.
Because you could define whatever you want for a table.
Yeah, so here we can define whatever kind of data we need in there. And that can use strings, integers, enums, vectors, lists, anything that's available in C++, basically, you can use here. And you can define indexing that can do all kinds of different queries in an efficient way based on what that data is. Yep.
Auto take it's a string or an int or anything, whatever it happens to be, whatever then the auto will just pick up.
The what will pick it up?
But, you know, find the type string normally or whatever the type is. Here it says on the third line message it says auto. That just means it can automatically pick up the type.
Yeah, I'm not sure what type an index function returns. It'd be some type. We could figure this out, but this is just.
Well, that means basically that C++ will figure out what it is.
C++ will figure it out.
Really, if you write it down, it's better. But now to figure out user value.
Yeah, it's probably some complex type that developers don't need to know about usually. And that's why they've got auto, to make it not so confusing.
Well,
I think.
it is a valid question.
Yeah.
When if you're trying to shield what kind of information is going to go in there, right? Yeah. Sorry. Yeah. Well, users are stupid.
So I mean, in C++, unlike JavaScript and many other languages, it's you have to define the type of every variable, every function, and that's what allows C++ to compile down to such small, efficient programs, because it knows exactly where to mix and match, and that's what allows it to be part of how.
What input user takes.
So, from what I understand and my not so big knowledge of C++, you define user as being of type name.
Yes. So name. This is the name is a class defined. Name is a class defined in the EOSIO library, which we pulled in here.
Oh yeah, totally.
Yep. No worries. Yep. So it's a type. So it wraps around a uint. So it's a uint at the end of the day.
And the auto means the compiler means you figure it out what it is. And because it knows that the primary key is a user, and user is of type name.
It's of type name.
Then it will become a name.
Yep, that's right.
Okay.
So this class has a few useful things. So firstly, the constructor of the class takes in a string, and that converts it properly into this uint value. So far there's no indexing functions for strings themselves, and that's why you've got this name class. It wraps around something that can be indexed. That's a big reason why that exists. So names are a much more user-friendly way to view data than integers. That's why this class exists. And names are used in a lot of EOSIO for names of tables, names of accounts, names of actions. These are all name types in EOSIO. So then we'll see as we go through this, a lot of this is much more user-friendly than looking at like a hash or an integer or something, which you see in a lot of other blockchains. So this is kind of what our table looks like in the database. We have two columns, a user value and a message value of name and string type, and we can put different rows in that table based on how we call that function. That function hi will update this table. And that primary key function allows us to create an index on this column, and it means we can query and search this column efficiently. So what's cool in EOSIO, and this is, I don't think anywhere else has this, is you can find as many indexing functions as you need. So you can't actually index on a string, but you can index on any other column. So a big problem, for example, in Ethereum, they only have one data structure called a map, and you can only search it by its primary key. That means if you want to create complex functions that may want to look through data and find a different value, you have to create like secondary maps that index back. It's very inefficient and very difficult. So this is very convenient, and it uses this particular data structure called a multi-index table defined in the Boost library. And that's what it stores it in the Node software. We won't go too much into that. What's useful is it allows you to define arbitrary data tables with multiple ways of indexing that data. Yeah, so this is that type here. Here we're defining this multi-index table. So it's of type. So this is defining a type, which we're going to use later. So the variable is messages table. The type is a multi-index table. And we give it a name for the table. So here we're using that name class again. And we give it the structure. So this is that struct variable that we just defined. Back here. So here is that structure right here. So that's what we pass into this type. And then we can use this type later on to access that table. Comprende? I hope. So review, we've just looked at the header file only. So that defines the actions, just defines them. It doesn't implement how the logic works behind them. It shows what the function is, the definition of it, what arguments it takes. It defines the table structures, what data goes into the table. And it defines a table type that we can use later. And that table data is stored in the EOSIO database. There's one EOSIO database for each blockchain deployed. And then each table in the database, no, we're not going to go through that too much. Yeah, I know. Okay, apparently we are.
Is there like a limit? Size limit?
Yeah, so we're going to get to resource management a bit later. So a blockchain has a finite amount of resources, like servers don't have infinite RAM, they don't have infinite capacity to have transaction of an infinite size, and we're going to see how that's dealt with in a bit. So each table in the database, it has a name of the table. It has an account that that table is owned by, and that's the same account that the smart contract is deployed to. So we deployed our smart contract to an account. That account controls the tables associated with that contract. Each table also has a scope, which is actually not a used feature anymore. It was intended for something else that's now not being used. So for all intents and purposes, we're going to use the same table name for our scope in every type and not worry about scope so much. It's quite a confusing topic. And it has a structure, and it has at least one indexing function that allows us to search through that table. So this is kind of what the EOSIO database looks like visually. So an account has a smart contract on it, so we deployed to our Hello World account. That contract defines the tables, and what's important here is that contract at this account has the ability to write to these tables and read from it. But it can only read from other accounts' contracts. So there may be another account called EOSIO.token with a contract on it that defines another table called stat. The contract at this account can read and write to these tables, but it can only read from this table. Make sense?
Right, yeah.
So that is the messages implementation definitions.